Let's start by talking about how to choose hypotheses for proportion tests. As an example, let's imagine that in 1990, 38% of Viterbo University students loved the food in the dining hall. We ran a new survey this year to see if that has changed. What should our hypotheses be? Take a moment to think about what your null hypothesis would be in this case. So in this case, I would argue that our null hypothesis should be that 38% of Viterbo students loved the food. That we have a p of 0.38 when we run our statistics. Now the next question is what should our alternatives be? Do we have a reason why we should believe that there should be an only positive direction? Should we only ask, is p greater than 38%? Or should we ask, is p less than 38%? Now these two cases might match to some actual events on campus. We could imagine if the Viterbo University hired a brand new 5-star chef, we might be a priori, or beforehand, expecting the value to go up of the students who love the food. If, on the other hand, the kitchen hasn't been updated since 1990, we might expect that to have gone down. Now, in most situations, we're actually going to be asking about either direction, or a two-tail hypothesis. This means that all we're asking is p not equal to 38%. So we want to know if it's changed, but we don't know which direction to expect that change to have gone. So let's imagine that in our new survey, 38 out of 80 students say they love the food. What is our p-value? How are we going to go about calculating this? Now, we want to set up our standard error and our z-score the same way we have for these other tests that we've done so far. So remember, the standard error for a proportion is p times q divided by n, and take the square root of all of that. If we plug that into our calculator, we get about 0.0543. Now remember, when you're doing these calculations yourself, to carry all of the decimal places that you have here. I did the calculations assuming all of the decimal places. It's just rounded to fit on the screen here. Our z statistic is just how different our value is from our null. So 38 out of 80 minus our null of 0.38. We divide that by our standard error, and we get 1.75. Now this is the value we're going to go to StatCrunch and plug in to get a p value. So if I pop over to StatCrunch and we go stat, calculators, normal. Now I'm going to remind myself of what that value was. It was 1.75. If I plug in 1.75 and click compute, I get this large value of 0.959. Now note that includes the body of the distribution, not just the tail. I want to invert this here to get greater than, and now I see that I have a p of 0.040059. Now if we consider what our alternative affects that, if we have a p or a positive only null hypothesis, our p is slightly less than 0.05. We might say that's a fairly rare occurrence, less than 1 in 20. However, if we have a either direction tail, remember that we need to double this value so we can take into account the area that is less than negative 1.75. Now we're up to about 0.08, but 8% of the time, and we may no longer think that that's significant. Now we might want to change our null hypothesis, for example, if we want to test against a different group of students. So what if we want to compare against the students at UW La Crosse? If we use a two-tail, because we have no idea which of the sets of food we want to set as our null hypothesis, we might change our null to be, say, 0.6. Now importantly, this is not an appropriate way to test if there is a difference between these two values. This is only an appropriate way to see if our value is different than the null. This approach assumes that the actual value of UWL is exactly 60%, and not that this is just taken from a sample survey. If we plug this into our z-score calculator, we just change our null hypothesis here, get a different z-score, which we would then put in over here, negative 2.3, compute, and now we can see that our p-value is 0.01 in one tail. If we double, it would be 0.02.